Morning, everyone. Today I plan to talk about the virtual memory. So let me share my screen. Virtual memory is a technique using the main memory as a cache for the secondary storage. For example, your disk. Nowadays, I think most people should have a SSD, but it's still disk. Uh, it's faster than the traditional HDD. You can consider a collection of programs um, simultaneously running on a computer. Um, all of them are share the same disk, and the total requirement um, the total requirement of their memory consumption may larger than uh, the capacity of a physical memory. So in this case, you need a virtual memory. Um, the physical main memory needed to contain only the active portion of the program. Um, for the inactive applications, their memory can be switched to the disk because you don't use them when you run something else. You only need to keep the active part, not even the entire part of the active application. You only need to contain only the active part of some active applications. This is so-called spatial locality and the temporal locality. The so-called temporal locality means you only store the active application. So the virtual memory can enable a set or a collection of application running on the same processor um, can share the same main memory. Also, in this way, each application can have its own virtual memory space, which is very important to their security. Because one application cannot easily access the memory space of some other applications. So in this way, we can protect one application from the other applications, or protect programs from each other. So the application can only read and write the portions of the main memory that have been signed to itself. So you cannot read and write others' memory parts. So all these features can be enabled by virtual memory. Virtual memory allows efficient and safe sharing of memory among multiple programs. Um, and you don't need to worry about the virtual memory when you do the programming because the virtual memory is managed by the operating system and hardware. You don't need to know, for example, you don't need to know the capacity of your physical main memory. Um, once you finish your programming, your application can run on a very large physical main memory machine or a machine with a small, very small physical main memory machine. So your programming model or your programming capability is not limited by the capacity of your physical main memory. And even for one application, it may dramatically and dynamically changed its memory footprint during its running. And the compiler sets each application into its own application space or address space. So the virtual memory translates the program's address space, which is a so-called virtual memory space, to physical addresses, enforcing the protection of a program's address space from other programs. The virtual memory also allows a single user program to have a larger memory than the physical main memory, because you can actually store some part of your address space onto the disk. So each memory block is a so-called a page. And each virtual memory miss is a so-called page fault. Typically, a page can be 4 kilobytes or 2 kilobytes. So this figure shows the structure or the framework of the virtual memory. For example, these are the virtual memories, and these are the physical memories. You can see the physical memory is actually smaller than virtual memory. And the virtual memory has multiple blocks, and each row indicates one block, so-called page. And the physical address also have multiple blocks, have multiple pages. The size of pages on virtual memory side and on the physical memory side are equal. So here one row indicates 4 KB. Here is another 4 KB. So you can easily assign this 4 KB to this physical blocks. But the physical memory may have a smaller number of pages than the virtual memory. In this way, the virtual memory has to store some pages on the disk. And only the active applications, active page are actually stored in the physical addresses. Physical address can be DRAM. Can be DRAM. So we assume that DRAM is faster than the traditional HDD or even the NAND gate flash. So these virtual memories are consecutive virtual memory. So you can see this is the page 0, page 1, page 2. These virtual memories belongs to only one application. So for another application, it also has its own consecutive virtual memory. Even your virtual memory is consecutive, your physical memory do not necessarily to be consecutive. So the consecutive virtual memory can be mapped to discrete isolated physical pages. You can see this page is actually stored here, but this physical page may not belongs to this application. It may belongs to some other applications. So only the virtual memory is consecutive. So this is the the virtual memory to physical memory mapping or translation. Because for simplicity, we only cover the 32-bit machine case. You can see that the virtual address here is from 31 to 0. You only have 32 bits here. So the 2 to 32 means 4 GB. Because the memory, no matter physical memory or virtual memory, are all byte addressable. If this virtual memory address is 32 bits, then we can see 2 to 32 is 4 GB. This is the capacity of the virtual address of an application. But you can see that the physical address is only 30 bits, 2 to 30, which is 1 GB. Nowadays you can also find this case on your mobile phone. For example, your mobile phone only have 1 G memory, but some application like Instagram may allocate 4 GB to store the pictures or images. So as you can see that virtual memory, both virtual memory and physical memory consist of pages. The size of pages are the same. So you can see that this page offset is from 0 to 11, which is 2 to 12 bits. 2 to 12 bits is 4 kilobytes. Why is 4 kilobytes? This is a 2, which is indicated you have a 4 here. This is a 10. 10 means you have a K here, so it's a 4K. And this is the case on the virtual memory. For the physical memory, you have the same case, which is also 4KB. So for the page offset, they are the same. For the virtual memory, you have virtual page number. For the physical memory, you have a physical page number. So for the virtual page number, you have a 2 to 32 minus 12, which is a 2 to 20. For the 20, this is a 2. 1 indicate K, 2 indicate M. This is a 0. So it's just a 1 M. You have 1 million virtual pages. For the physical address part, you have a 2 to 30 minus 12, which is a 2 to 18. 1 indicate K, 8 indicate 256. So totally you have a 256K physical page. Again, this number is larger than this number. So not every virtual memory page can have a physical page. So they are not a one-to-one mapping. Some of the virtual memory may not have a physical page. And we need a translation here. So for simplicity, people call the virtual memory page as the page, call this one as page. They call the physical memory page as a frame. We will use both words in the following slides. So when you write an application, your application generate a memory request. When the application generated this memory request, it's a virtual address. How to translate this virtual address to the physical address is a very important issue because you have to guarantee a very fast translation. Otherwise, you just prolong the latency of each memory access. If your one, for example, you request for one virtual memory page, if your virtual memory page can have a mapping corresponding physical page in the main memory, it's called a page heat. You have a heat here. If you find out that your virtual page is not in the memory, which means you don't have a physical page in the main memory, that's so-called page faults. So in order to handle a page fault, you need to pay millions of cycles. So once you have a page fault, it's very slow. A page fault means that you find out your virtual memory page is actually in the disk. This is the reason why we request a large granularity, which is a page 4 kilobytes during the physical virtual memory translation. Because each your memory request is only 64 bytes. So once we handle 4 kilobytes, in this way, we don't need to do the 64 bytes every time. We just handle 4 kilobytes once. Assume that your application have a strong spatial locality. So in this way, we can save a lot of time. And of course, on the normal PC, you have 4 kilobytes or 16 kilobytes. On some server, they prefer large page size because they have a larger physical memory capacity. One page may cost 64 kilobytes on the server, but on your mobile phone, it's only 1 kilobyte. So we will talk about how to reduce the page fault rates. It's similar to your cache. You also need to do the replacement to guarantee that you have a larger, to guarantee that you have a smaller page fault rate. This page fault rate is similar to the miss rate, cache miss rate. By a better replacement policy, you have a smaller page fault rate. Besides the page fault rate, you also need to improve the access latency of each memory access, which is the virtual memory to physical memory translation latency. So the page fault is handled by your operating system. Unlike the cache, which are all managed by the hardware, the replacement policy of pages is managed by the operating system. So Windows and the Linux may have a different replacement policy. So reducing the page fault is very important to your memory access latency. So the operating system can use different policy to do the replacement and a different structure, data structure, to track the page usage. Typically, this data structure is called a page table. The page table is stored in the main memory, in your physical memory. Besides the real virtual pages, a page table for each application is also stored in the main memory. So this is so-called overhead because this is a, some free-for-all data structure to help the operating system to track the usage of the pages. So this is a pure overhead. So which means that you have to guarantee it. You don't have a very large overhead on the page table. The page table must be small and fast. So the page table contains the virtual to physical address translations. An entry contains the physical page number for virtual page for that virtual page if the page is currently in the physical DRAM. So to indicate the location of the page table in the memory, the hardware has a page table register to point to the start of the page table. And the page table plus PC plus the register specify the state of a program to allow another program to use the CPU. This state is saved. Restoring this state enable the program to continue its execution. So you can see that each application's page table register is actually related to its program counter. So by the program counter, different application may have different values for their program counters. So in this way, they can distinguish, each page tables. Application A has its own value of a PC program counter. So it has its unique page table starting address. Application B has its unique PC value. By adding different PC values, each application has its unique page table starting addresses. So when we say a process or an application or a program is active when it's running on the CPU, otherwise it's inactive. Operating system activates a processor by loading its process state, including the PC. Including the PC table, the page table register to, enable it to run on the CPU. Because each memory request need to go through the page table, need to do the translation from virtual address to physical address. So in this way, all the memory access is actually defined by the page tables. So if the operating system finds some memory request that is not safe, it can easily deny this access by not doing the not translating the its address to physical address. It's a virtual address to physical address. So since every request need to go through the page table, you can do a lot of manipulation on the page table to deny something or to accelerate something. If you want to give some application higher priority, then you can always keep its page table in the physical memory. So in this way, the request from this application can be significantly accelerated. And of course, the operating system need to load only the page table register with the pointer to the page table of a application to be run. So each process has its own page table. But all the page tables are managed by the operating system. So each program or each process has the same virtual addresses. All their virtual addresses starting from a 0 to 4 GB. We calculated this example in the previous slides. Because in this slides, we assume that each application has a 32-bit virtual address. So all the application can have the virtual address from 0 to 4 GB. But you can concurrently switching maybe 4 applications or 8 applications. So totally, these applications have maybe 16 GB or 32 GB memory consumption. But in fact, you only have 1 GB for the physical DRAM. And of course, if you want to support more applications, you will have more collision. Collision means you have a lot of page faults because your physical memory is very small. And since the operating system can manage all the page table for all of the applications, so in this way, we can isolate each page table. We can, deny some memory access. We can accelerate, give some application higher priority. In this way, we can protect each program. So this is one example of your page table. The page table register record the starting point of your page table. So this is your starting point. Because the page offset are the same, so the content inside each table do not need to be translated. You can directly copy the address here to here. Why? Because each page is 4 kilobytes here and 4 kilobytes here. So you don't have to do the translation inside each page. All you need to do is to translate these 20 bits virtual page number to this 18 bits physical page number. This is all you need to do. So one naive way to implement this is just a lookup table. So you look up this table by this 20 bits, and then the result is 18 bits. You done the translation. This is the easiest way to do this. You can see that because this page table is inside the DRAM, inside your main memory, once you do a translation, you have to access the DRAM. And because this is if you want to implement this by a naive lookup table, your lookup table at least should have 2 to 20 entries, which is a 1M entry table. Apparently, this is a very large table. So this is managed by the hardware because this is a hardware register. This part is managed by the operating system. And besides, so we just talk about the size of the table. Besides the virtual memory and the physical memory bits, these 20 bits, this is 18 bits, we also need some state bits to indicate some other information, which for example, whether this page is in the memory or in the disk or in the SSD, right? These are some peripheral informations. And these informations also occupy some capacity, some space. Particularly nowadays, you have the real HD disk and the flash disk. You may have a lot of disk. So the operating system can actually mapping all the virtual address to the disk when it creates the program or the process. So the disk space is a so-called swapped space. Once you installed something on the Linux, you will have this. Or the Linux operating system, you will find some swap disk, a swap space. Operating system also create a structure to record where each virtual page is stored on the disk. It's a part of the page table. Or some other data structure indexed in the same way as the page table. So either you have a combined page table or a separate page table to store the information in DRAM and in the disk. So this is the the real picture of the page table. You have a register. I'm sorry, this is not a register. You have a register here. The register record the starting point of your page table. The register here is the hardware. Once you have a memory access, it has the virtual page number. By this virtual page number, you can look up this table, and then you can know whether your data is stored in the physical page or the disk. So you can use 1 bit to indicate that. If it's a 1, then it's in the DRAM. If it's a 0, then it's in the disk. Virtual page number is used to index the page table. So the valid bit is a 0 indicate the page is in the disks, in one disk. And all the page table is managed by the operating system. Operating system may make a page table for each applications. So when all the page in the main memory, once you have a page fault, the operating system need to pick up a page to replace. The replaced pages are often written to the swap space on the disk. You can also use the least recently used policy to do the page replacement. But in order to maintain this least recently used information, operating system need to do a lot of writes in the main memory. So it's a very expensive. Some approximation algorithm is used actually in the current system. Some computer also use provide a use bit or a reference bit to indicate whether a page is accessed or not. So by this bit, you can easily understand whether this page is accessed or not. And the operating system may periodically clear this bit and set this bit. If this bit is not set, which means that this page is never, I cannot say never, but is not accessed during this particular period, then this page is a very good candidate to, replace. You can kick out this page based on the so-called temporal locality, because in this period, this page is not a hot page. We can replace it. So we do this calculation before. We calculate if the virtual address is 32 bits, each page is 4 kilobytes. Totally, we have 2 to 20 entries. If each entry is 4 bytes, so this is 1 M. If each entry is 4 bytes, then totally we have 4 M bytes for one page table. So this is how you can calculate the size of the memory overhead of your page table. And this page table is only for one process or for one application. You can easily see how many applications or how many processes are running currently in your computer now by some administration tool. You may find thousands of these. So if you are running 100, 100 or 1,000, let's assume 100. So 400 MB is actually consumed by your page table, all the page tables. This is apparently not acceptable because this is too large. It's large. It's large when you have a 16 gigabyte physical memory. It's even larger when you have only 1 GB physical memory. So you can see that 40% of your physical memory is actually consumed by the page tables. If one page table is 4 MB, that this is not acceptable. Again, if you adopt a read-through policy, your CPU may even be slower. Read-through means once you modify some content in the main memory, you will write to the disk. So the read-through is impractical. then you have to use write back. We have similar concept in the cache. In the cache, we study whether you need to write back to the main memory. Here, when we talk about the write back, we consider whether you write back to the disk. When we modify something in the main memory, the write back means only when we replace this page or evict this page to the disk, we write back to the disk. So the write back is more efficient than the write through, because write through you need to write every modifications. Write back only write the last modification to the disk. Even the write back is very time consuming. We typically use a dirty bit to indicate whether this bit is modified or not. If this page is not modified, we just throw it away. We don't have to write back. We only need to write back the modified page. We have that table. We explained that page table. The page table is in the main memory. Why? Because your page table is 4 megabytes. For some low cost computer, your cache cannot have 4 megabytes. So the 4 megabytes data has to be stored in the main memory. Each memory access needed to do a translation, which means that each memory access need to go to the main memory once to do the translation, and then go to the main memory again to get the real data. So each memory access will be translated to at least 2 memory access. That's very slow. So in this way, this is why this is so-called twice long. So in this way, they propose lookup faster address translation. This is TLB. We talk about the TLB in our cache slides. Here we will explain that again. Because we have the temporal and the spatial locality, which means that when we do a translation for one virtual page, it's very likely we will do the translation for the neighbor of this virtual page. Or maybe after 100 cycles, we will do this virtual page again. So this is so-called spatial locality. When we want to do the translation for its neighbors, it's a so-called spatial locality. When we want to do the virtual page translation 100 cycle again, this is called a temporal locality. Because of these two types of locality, we can have a cache named the translation Lucas set buffer to keep the recently used translation. So the cache, the TLB is very small. Once you have the virtual page number, we go to the TLB, and then we can go to the physical memory. In this way, we don't have to go to the page table every time. Once we get a hit in the TLB, we just have one memory access to the physical page. Otherwise, we have to go to the page table first, and this guy also in the main memory, and then finish the translation and go to the real physical memory again. And this is two main memory access. But for the TLB, this is an on-chip cache. We go to the cache once, and then we go to the physical memory. Here is the difference. So the TLB significantly improved the memory access latency. And the TLB also stores some information, whether this page is modified, whether someone accessed this page before, whether it's in the physical memory or in the disk. these free-flow information are the same as the free-flow information on the page table. So every memory access, one reference means one memory access will look up the TLB by its virtual page number. Once the TLB hit, we get a physical page number. And whether this page is dirty or not. So the TLB is a cache for the page table. Once we have a TLB hit, everything is good, is fast. Once we have a TLB miss, either we have that, either this page is actually in the physical memory. One page is in the physical page memory, but we don't have the translation in the cache. This is one case for the TLB miss. We don't have the translation in the cache. This is one case of the TLB miss. Or that page is not in the physical memory. That's so-called page fault. Or we have a true page fault. So you have a different cases for TLB miss. One TLB miss may trigger page faults, or you just fetch that translation to the cache. It can be slow and can be very fast. If you have a true page table fault, then the operating system need to fetch that table, that page from a disk to the main memory. In that case, it's slow. Otherwise, if you have that page in the physical memory already, but you don't have the translation in the cache, then you just directly fetch the translation to the cache. That part is very fast compared to the true page faults case. At the TLB miss, we need to select the TLB entry to do the replacement and copy the reference 30 bits back to the page table, because we may, modify this reference 30 bits, and the information on the page table may not be the latest. So in this one, we need to do the write back. This is the cache write back. And then we can evict that TLB entry. TLB is very efficient because some applications have very strong spatial and temporal locality. And the write back only happens when you actually evict a TLB entry. When you modify something in the TLB, you don't need to do the write back. Only when you decide to evict something from the TLB, you do the write back. So this is the typical information of TLB. TLB is only have maybe sometimes 16 entries. It's a fully associated cache. Typically, it's a fully associated cache. Nowadays, for the server end, you have a set associative TLB. And the block size is also small. It's only 4 to 8 bytes. Heat time is very fast. Only maybe 1 cycle or 0.5 cycle. So by such small heat latency, you cannot have a very large TLB. Why this? We explain this in the cache slides. It's impossible for a very large cache to do such fast lookup. And this is the miss penalty, and this is a miss rate. You can see the miss rate is very low. This is for normal applications. You can write some very random access application. In that way, if an application has a super random memory access, then the TLB miss rate will be very high, because when we design the TLB, we assume we have very strong spatial and temporal locality. Once we get the virtual address, once we generate a memory access, we look up the TLB. You can see that we concurrently, compare all the entries here. When we concurrently compare all the entries here, it's a fully associated cache. Because when we do a fully associated cache, we have to keep the TLB size small. Otherwise, the lookup will be very long. Latency will be very long. And then we find the heat here. We get the physical page number here. We directly copy the page offset here, because the page size are the same for virtual and physical memory. We don't have to do translation inside each page. So by these two parts, we can have the physical address. Once we have the physical address, we can use the physical address to look up the cache. Why? Because each memory entry have a different physical address, because different data is actually stored in different physical addresses. And the cache is actually indexed by the physical address. I don't think we discussed this a lot when we talk about cache. But here, once we understand the TLB, we can know that only after a TLB translation, we can do the cache lookup. And we index the cache by physical address, because different data are stored in different DRAM addresses, physical addresses. In this way, it's easy for the hardware to manage the cache. Otherwise, if we use a virtual address to do the index, all the application may have the same virtual address. Why the same? Because everyone have from 0 to 31 bits virtual address. So everyone has the address from 0 to 4 GB. If two applications try to request the memory address all zeros, then two applications may read the same piece of data. But this is wrong, because this all zero virtual address may be mapped to different physical location for different programs. So the virtual address are fake. You can only use the virtual address inside that program. But the cache is shared by all the programs. If you use this data piece of address to look up the cache, two programs may find the same heat. So that's wrong. This is the reason why we use physical address to index the cache. So each TLB entry is 64 bits, 20 bits tag. Why 20 bits tag? because each virtual page number is 20 bits. We need to compare all these bits to decide whether this is a hit or not. So 20-bit tag. And the corresponding physical page is, although the physical page number is 18, we also have some, valid bits, dirty bits. These bits, totally we have another 20 bits. This is the reason why each entry is 64 bits for the TLB. And the TLB is a fully associated cache. We have a 16 entry here. It's shared between the instruction and the data. And we directly copy the address inside each page. We don't do the translation for the value inside pages. After we get the physical address, we can use this part as the tag and this part as the index to look up the tag. And then we can have a cache hit. So we calculate each page table may occupy 4 megabytes. Which is very large. If you have 100 applications, totally you may pay 400 memory capacity only for the page table. So in this way, people try to reduce the size of a page table. They propose so-called hierarchical paging. So from a previous slides, we know the virtual page is 20 bits. So they divide this 20 bits into 10 bits here. They use the first 10 bits to index a so-called outer page table. And they use another 10 bits to index the displacement within the page of the inner page table. So here is one example. So they divide the entire page table to an outer page table and a so-called inner page table. They use the first 10 bits to index a table, and then it the lookup results is actually the starting point of the second level inner page table. The result is here, the starting point of the inner table, and it used the second 10 bits to do the lookup inside the second page table, inner page table, and then they get the physical page number. So instead of the entire large one, they divide the large page table into two small page tables. Because we have 10 bits here, we use this 10 bits to index this guy. We only have 2 to 10 entries here. And this one is also 2 to 10 entries because these are also 10 bits. So this is a 1K. This is another 1K. Traditionally, if we use this 20 bits to do the index, we have 1M. But in this hierarchical paging, we have 1K here, we have another 1K here. So we reduce it from 1 megabytes, 1 M entries to here 1K entry plus another 1K entry. So this is the overview of the hierarchical paging. We have a 1K here, and this is the inner table, also 1K for each. How many totally we have? 1K. So 1K multiply 1K is still 1M. We don't actually reduce the size of a page table. We just break the large 1M entry into 1K pieces. Because your application have a so-called spatial locality, we can only, we can only keep a part of your page table in the main memory. The other parts can be stored in disk. So even now it's more complicated or complex. Even your page table can have so-called page fault, because only a part of your page table is inside the main memory now. But in this way, we can only keep a part of your page table in the main memory. We reduce the page table overhead. We talk about a virtual address indexed cache. The virtual address indexed cache is fast because you don't need to do the TLB lookup and then look up the real cache. You can directly use your virtual address to look up the cache. But again, once you do the context switching, once you switch from one application to another application, you have to flush all the content in your cache, because all the applications have the same virtual address. Only in this way you can maintain the correctness. So the overall performance of the virtual index cache or virtual address cache may not be good as the physical one, because you do flashing a lot. People have a compromised solution, which is a virtual indexed but physically tagged cache. Virtual indexed can enable to do lookup fast, but when you do the lookup, you still need to use the physical address to compare whether this is the real data you are looking for. By the virtual address tagged, you can maintain the correctness, but you can do the lookup earlier. You can overlap this lookup and the data comparison. This is a faster than the pure physically indexed cache. And that's all for the virtual memory. For the virtual memory, I know this is difficult, but I truly hope that you can understand this figure. At least then you need to understand what's a page table. The page table record each virtual page, whether this virtual page is in the physical memory, in the physical DRAM, or in the disk. And at least you need to understand why we need a TLB. The TLB is used to accelerate the translation from a virtual address to physical address. I hope you can understand this this picture. If you have any question about the virtual memory, about this picture, you can ask now. You can also email me. Any question? If no question, we can finish today. Thank you very much.
Thank you.